So you want to learn how to find the HCF of two numbers using Euclid's division algorithm. Now to do that, let me begin with a question. Do you know how to find the HCF of two numbers, say 32 and 12? Now depending on which standard I was asked this question, I had different methods. In 6th standard, I was taught how to count all the factors. Like a nice obedient child, I would write 1 into 32, 2 into 16, 4 into 8 and so on. Do the same for 12 and then just count what the common factors are, 1, 2, 4, and then pick the biggest one from them. That's it. That's my HCF, the highest common factor. And this is the most intuitive method, but in 6th they used to give us all small numbers, so this was easy to do. But if the numbers become big, this is really hard. It's very long at least. So then they taught me how to do prime factorization. Do you remember prime factorization? That's just writing down this number in its prime factorized form and then picking the minimum powers of each of the prime factors and multiplying them. That gives you the answer as well. The same HCF 2 squared, which is 4. But now it's time to learn a method that's a recipe rather, because whenever I think about the word algorithm, in my head the word I have is as a recipe to find the HCF once again. So you may be wondering, why do I need to know more than one methods? One argument is because it's useful, especially when the number becomes really big. This method, the Euclid's algorithm, works faster. The other one is actually really beautiful. If you notice what's happening here, and if you really try to understand why this recipe works, it gets really beautiful. So, but before doing that, let's first see what the recipe is. What is this recipe? This recipe says, okay, so you want the HCF of these two numbers. I don't know why you want it, but you want it. So 32, 12. This is one way of writing this big problem called how to find the HCF of 32 and 12, HCF of 32, 12. Now what this recipe says is check if 32 is divisible by 12. If it is divisible, you're done. 12 is your HCF. Now think about that. That's actually obvious. If one number is divisible by the other, then the smaller number is the HCF, right? So do that here. Is 32 divisible by 12? Unfortunately, it's not. We can't go home. We're not done yet. So then it says, interesting. So if this number is not divisible by this, then what you do is forget about this question. Forget about finding the HCF of 32 and 12, but find this other HCF. Find the HCF of, and watch closely over here, the smaller number, which is 12, and the remainder that you get if you divide the bigger number by the smaller number. And what is that in this case? If you divide 32 by 12, the remainder that you get will be 12 will go twice, 24, and then there will be 8 remaining. Because these numbers are small, we can do it in our head. It says, the recipe says, find this HCF. You're like, okay, I can find this HCF, but why should I find it? And then the recipe will tell you, you find this because this HCF and this HCF will be exactly equal. So if you find this, it's as good as finding this. Now notice that the recipe is not yet told you why this works. It's just telling you, hey, trust me. The HCF of this number will be the same as the HCF of these two numbers will be the same as the HCF of these two numbers, right? Now we will look at why this works later, but let's first see how to use the recipe. So, okay, you say fine, maybe this HCF and this HCF are the same, but even then I started with a HCF problem. I asked you to find the HCF of 32 and 12. Now you give back another HCF problem, find the HCF of 12 and 8. How useful is that? But notice that the numbers have become smaller. And more beautifully, you will not find the HCF over here. You will do the same thing again. Because if this HCF is equal to this one, you can apply the same step again. You will ask, okay, you want me to find the HCF of 12 and 8. Is 12 divisible by 8? If it is, 8 would have been the HCF of 12 and 8. But it's not. So do the same thing. This is equal to the HCF of, once again, the smaller number, and the remainder that you will get if you divide the bigger number by the smaller number, which in this case, if you divide 12 by 8, you'll get a remainder of 4, because 8 will go once. Now once again, you ask the same question. Is 8 divisible by 4? And in this case, the answer is yes. 4 will be the HCF. And if you actually think about it, HCF of 8 and 4 is a really simple problem, right? You know that the answer to this is 4, because 8 is divisible by 4. But the beauty here, I actually want the 4 to be in red color. But the beauty here is that it's not just the HCF of 8 and 4, it's also the HCF. 4 is also the HCF of 12 and 8, and 4 is also the HCF of 32 and 12, which is the original problem that you began with. So Euclid's division algorithm has given you the HCF of 32 and 12 without doing prime factorization, without having to know what each of these factors are. So now you've just learned a new recipe. We haven't yet seen why this works, but let's use the recipe a couple of times to cook a couple of new dishes and then learn why it works. So let's pick some other two numbers, not 32 and 12, maybe something slightly bigger. Maybe we can pick, let's see, maybe 627 and 45. Now I want you to pause the video and watch what happens as you use this algorithm now, or the recipe now, to find the HCF of these two numbers. I'm going to do it. So HCF, I want the HCF of these two numbers, 627 and 45. 627 and 45. Now I don't think one is divisible by the other. It may be, but because these numbers are big, I'm not going to sweat it. I'm just going to do it and see. 627 divided by 45. If I get a remainder 0, I'll go home very happily. I don't think that's going to happen though. So I have 45 going once, and I have a 7 over here, and then 1 over here. 17 that's remaining. And then I have 177. That's the remainder. Now 45 goes probably 3 times there. And then I can find 5 3s are 15. And then 4 3s are 12. So 135. And then I can find my final remainder. So 7 minus 5 is 2. 7 minus 3 is 4. And that's it. So it's 42. So it is not divisible. So clearly 45 is not the HCF of these two numbers. But Euclid's division algorithm says, that's okay, don't feel bad. You can find the HCF of the smaller number, 45, and the remainder when you divide the bigger number by the smaller number, which we just did. It's 42. So 45 and 42. Now go and find the HCF of these two. Now once again, you can do some other method now, maybe because you feel the numbers are smaller, but I'm just going to use Euclid's division algorithm again because it's fun. So now find the HCF of the smaller number. Now why am I not checking? Because clearly 45 is not divisible by 42. If it were, 42 is my HCF, but it's not. So I'm going to use the smaller number. In this case, that's 42. And the remainder that I will get if I divide 45 by 42, which is 3. 42 will go once, and I'll get my remainder to be 3. So 3. And now I ask my classic question again. Is 42 divisible by 3? And in this case, it is. 4 plus 2 is 6. So the sum of the digits is a multiple, so it's divisible by 3. And there I have it. The HCF is 3. And therefore, I can jump all the way back and say the HCF of these two numbers is also 3 by the magic of the Euclid's division algorithm.